Air and the atmosphere. An empty drinking glass is not really empty. It contains air. It's common to think that air has no weight or mass, but the truth is that it has a surprisingly large mass. For example, an empty cubic meter cardboard box. That means all sides are 1 meter. That means its width and its depth is 1 meter, its height is 1 meter. So an empty cubic meter cardboard box will weigh between 3 to 5 pounds. The air inside the box is 2.75 pounds. So a big portion of the weight of this box is the weight of air. It's not weightless or massless. We don't feel the weight of the air mass only because we are immersed in an ocean of air. To give you a sense of this, I want to go over an analogy of a water balloon in a swimming pool. A water balloon has a significant weight when compared to an air balloon the same size. If this water balloon is taken into a swimming pool, the water balloon feels weightless. This is because of Archimedes' principle. That is, the water balloon is unconscious of its weight in water. What this means for us is that when we walk around, we don't notice that air has weight because we're immersed in air, just like the water balloon is in the swimming pool. The atmosphere. The thickness of the atmosphere is 30 kilometers, which is equal to 18.6 miles. Over here on the right, I have a picture. Mount Whitney is about 10 kilometers high. And if you go up to 20 kilometers, that's 90% of the atmosphere is below 20 kilometers. And if you go up to 30 kilometers, which is 18.6 miles, 99% of the atmosphere is below this line right here. And what you're seeing here is that when you start to look at this atmosphere, how thick is 30 kilometers? Because typically that's what people say is the top of the atmosphere. So the thickness of the atmosphere, this is equivalent to roughly driving from downtown Watsonville to downtown Santa Cruz, because that's about 28.5 kilometers or 17.7 miles. That's the thickness of the atmosphere. You may not realize this, but the thickness of the atmosphere is extremely thin. And to get a sense of that, we compare it to the size of the Earth. So the thickness of atmosphere divided by the radius of the Earth, which is 30 divided by 12,800, is 0.234%. So less than half of a percent is that due to the atmosphere. It is tiny, very, 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 very thin. So because this is so thin here, you could say that the atmosphere is like the skin of an onion peel. Question: why does the Earth have an atmosphere? The thickness of our atmosphere is determined by two factors. The first factor is the kinetic energy of the air molecules. The sun heats up the air molecules and gives them energy. Some of them are slower speed molecules, and they have a tendency to stay close to the Earth's surface, while the fastest ones go to the very top of the atmosphere. So in other words, the sun has a tendency to spread the air molecules out. The other factor is gravity. As air molecules spread out, it is gravity that stops the air molecules from leaving the Earth. So therefore, we have an atmosphere. As a counterexample, the moon's gravity is too weak to keep any gas molecules. Therefore, the moon does not have an atmosphere like the Earth does. Pressure and atmospheric pressure. Let's define pressure. Pressure is equal to the force divided by the area. So to give you a sense of what do I mean by this pressure equation, suppose we have two rectangular wooden blocks that weigh the same. And I put one of them standing up and the other one laying down. So the red one here is standing up, the orange one here is laying down. But if you look at the area of contact, the one standing up has a smaller area, the one laying down has a bigger area. Because these two blocks weigh the same, they apply the same force onto the table that they're laying on, but their pressures are not the same. So both of these blocks have the same force, but the red block has a smaller area, but a smaller number in the denominator means you have a higher pressure. On the other hand, the orange one has a bigger area, so it applies a smaller pressure. So in this case here, area determines how big the pressure is. One example is stepping on one's finger with a wide sandal. That has a much larger area versus high heel shoes, which have a very small area. Clearly, the high heels shoe will apply a larger pressure and it's going to hurt a lot more. You're getting a higher pressure because of the smaller area of the heel. Another example is, why do people sharpen knives to use in the kitchen? The sharpening process decreases the area that will allow you to apply a larger pressure to cut something better. Units of pressure measurement. Our definition of pressure is that it's force divided by area. Remember that force has units of newtons and area have units of meters squared. So then a unit of pressure then is a newton divided by a meter squared. And because this shows up so much in pressure measurements, it's defined as 1 Pascal, which is equal to 1 PA. 1 Pascal of pressure is a tiny, tiny unit. To get a sense of how much a pressure of 1 Pascal is, imagine spreading a stick of butter. That's about a newton in weight all over your kitchen's table's top. That means you got a very, very, very thin layer. The weight of that butter acting on your kitchen table is about 1 Pascal. So 1 Pascal of pressure is not very much. And typically, ordinary pressures in everyday situations come in hundreds of thousands of pascals. The standard pressure that people typically refer to is 1 atmospheric pressure, which is typically written as 1 atm, which is 101,000 pascals. There's a couple of other pressures that we should look at. Typically, a car tire is about 2 atmospheres, or 200,000 pascals. Spiked heels on a floor is about 1,000,000 pascals, or 10 atmospheres, and the deepest ocean trench is about 100 million pascals, or 1,000 pascals. We now define roughly what atmospheric pressure is. Atmospheric pressure is the weight of air acting on you. Now, to calculate this thing mathematically, I'll give you a conceptual example of how we do this. To get a sense of what this means, consider the following example. A cubic meter box of air weighs about 3 pounds. So if I have this little box, I'm going to say that that box weighs around 3 pounds. The top of the atmosphere is 40 kilometers, or 40,000 meters. Imagine that there's this little tiny person who's holding up a box, and that box is 1 meter in height. How much weight is he going to feel? So his weight that he feels is 3 pounds. So if I now put a second box of air, that box is not going to weigh 3 pounds, it's now going to weigh 6 pounds. So how much does he actually feel? He feels 6 pounds. Since the atmosphere is 40,000 meters, if I was to put 40,000 boxes on top of this little person, how much weight would this person actually feel? It would be 3 times 40,000, which then would be 120,000 pounds. But there's a correction here. It turns out that the atmosphere is not uniform and it thins as it goes up. So what's the actual value? The actual weight of the atmosphere is 22,500 pounds, which is the same as 100,000 newtons. That's how much the atmosphere weighs. The weight of the air bearing down on us is the cause of atmospheric pressure. So by definition, atmospheric pressure, which I typically write as P atm, is the weight of the air, and that's 100,000 newtons. The area of a box was 1 meter squared. That's how I get 100,000 pascals. It is very hard to understand how incredibly large amount of pressure this is. Question: if this pressure is so large, why doesn't this pressure simply crush us, like a car rolling over a grape and crushing it? The answer is that air is a gas, and it will take on the shape of its container, just like water does. Now imagine that I have this cartoon figure. The fact that your mouth is open, air goes inside your body. Once inside your body, it produces a pressure that's pushing out. So that's the pressure of the inside. But then I have the air from the atmosphere that's pushing inwards. And what you find here is that we get into a state of equilibrium. This equilibrium says that the pressure inside must be the pressure of the atmosphere outside. You will not feel anything because you only notice pressure differences. So the pressure difference is zero. So you don't notice the atmospheric pressure. Now that we have defined atmospheric pressure, how is this pressure actually transferred to objects? The answer is collisions. That is, atmospheric pressure is the collisions of air molecules applying a force per unit area on an object. The reason why one feels atmospheric pressure acting on you is due to the numerous collisions of air molecules colliding with your skin. One of the most important properties of pressure is the following. Gas pressures always move from a high to a low pressure region. That is, if I have this red region, which is a high pressure, and I have this blue region that's the low pressure, the system always moves from high pressure to low pressure. That is, if a system changes such that there is a pressure difference, the system always moves from a high to a low pressure region. For systems involving atmospheric pressure, here's what usually happens. I have a high pressure region and I have a low pressure region. The high pressure region, we always know that it is atmospheric pressure. Our goal now is to figure out what caused the low pressure. That is, we want to figure out the cause of the low pressure region. To understand the cause of the low pressure region, we use the ideal gas law to isolate the cause. There are three different causes. The first cause is the number of air molecules. If I have more air molecules, there'll be more collisions, so therefore I have a higher pressure. The second cause is temperature. It turns out that temperature and kinetic energy are related. If I have a higher temperature, I have a higher kinetic energy. And finally, the third parameter is the volume. If I have a smaller volume, then the molecules will collide more compared to a larger volume, will they collide less.